Thank you for coming. Talking about pseudorandom states and some applications of this concept, no cloning theorems for them, and we can construct money schemes based on these pseudorandom states. And my name is Zhengfeng Ji. I'm from UTS, University of Technology, Sydney. We have a center called Quantum Software and Information. And this is a joint work with Yikai and Fan. So because this is a mixed audience with people from different backgrounds, I would spend a few minutes talking about basics about pseudorandomness, even though it's one of the few foundations for modern cryptography. So classically, pseudorandom objects are like objects look random to computationally bounded adversaries. And for example, pseudorandom generators are like a function G here, and the function maps L-bit strings to 2 L-bit strings. It stretches the length of the string. And the requirement is that if you randomly input X and get apply G to the input, and then get GX, and it should look like a random 2 L-bit string, and there's no efficient algorithm or distinguisher that can tell these two situations from each other. And one basic fact we know is that PRGs exist if one-way functions exist. And there are also other interesting constructions like functions and permutations, pseudorandom functions. The basic idea is you have you consider the family of random functions where random function is for each of the input you assign a random value from the range independently, and use this computational indistinguishability. You can have a definition for pseudorandom function. You have a key, and then you get a function, and the idea is you would require that there's no polynomial term algorithm A that would tell you tell apart from this pseudorandom function and truly random function. If you consider one-to-one functions, then you have permutations, and also there are constructions for pseudorandom permutation. Then these are important constructions and used in stream ciphers, block ciphers, and message authentication in classical crypto. So the next question is, we are like a quantum crypto conference. Why should you consider pseudorandomness? Because this seems to be like a weaker version of randomness. We know that in a lot of talks in this conference, there are ways to generate randomness from quantum mechanics, and we can even certify them depending on the situation or the setup. So why should we care about pseudorandomness? Well, the answer is about the efficiency. If you think about random functions with n-bit input and n-bit output, there will be 2 to the n times 2 to the n number of such functions, and even write down one of the functions would require exponential number of bits, so it will not be efficient. And also the similar argument would apply to the quantum states, the Hilbert space, the largest space that we all know, and you would need exponentially many bits to have a good approximation of random states. So, and in fact, there have been a lot of research in this direction, considering pseudorandom objects against quantum attacks. So basically, the change is that now we would need stronger assumption that quantum one-way function exists, and once you have this assumption, you would have all this PRGs and PRFs and PRPs to be quantum secure. So you might think you have an assumption, but this is a very minimal assumption that you can have. And if you don't have quantum secure one-way functions, there's nothing interesting that this conference can have. So the main topic of this talk is about pseudorandom quantum objects. So for example, the PRGs, PRFs, and PRPs, so they're all classical objects in a sense, functions or strings. What we start to investigate is the set of objects that are intrinsically quantum, like quantum states or unitaries, but in this talk, we'll be focusing on quantum states. So what would be appropriate definition for pseudorandom quantum states? So first, we have a very good understanding of what random quantum states look like. They are high random pure states. And so one way of defining pseudorandom states is, the straightforward way is you just have a family of states, and it's computationally indistinguishable from the high random state, which give you essentially the maximally mixed state. If you average over all the possible states. And this definition has been used in certain settings, and Yishou Chen and Kaiming, Qingyi, and Salio Xiaodi has used this definition in their study. But what actually independently we study this definition, and we found it not so satisfying because it doesn't capture a lot of properties that random states we have, we know about. For example, we know that random states are no clonable, and typically the random state would have a high amount of entanglement. But if you are happy with this definition, then you don't have no cloning and you don't have entanglement. For example, you can consider a family of states that are only in the computational basis, and this would satisfy the definition exactly. And after thought about a bit on this, and we found that essentially the problem for quantum is that we don't have cloning, right? Classically, you don't even bother to ask for multiple copies. We want to distinguish these two situations. But quantum mechanically, because there's no way to clone, you have to give it to the distinguisher. So in our definition, it's almost the same. The first one is if you should be able to efficiently generate the states when you know the key. The second thing is that pseudo-randomness. It means that there's no efficient algorithm can tell these two situations. One is the pseudo-random family, and what the other is the her-random family. Even you have like arbitrary polynomial number of copies to the states. And once we have the definition, and we can actually show many properties, and like the problem for no cloning and entanglement would be fixed. But since it's obviously a stronger requirement for this definition, why should it even exist? We're defining a set as non-empty. And so we have to give you a construction, and so our idea is you use quantum secure pseudorandom functions or pseudorandom permutations to give families of pseudorandom states. So this is one of our candidate construction, and so basically, if you look at the formula, it's equal superposition with faces, and the faces is related to pseudorandom functions. I don't have time to show you about the details, but you can show that this family is efficiently generatable, and you can argue that there's no efficient algorithm can distinguish this family from the high random states, no matter how many copies you are given to the distinguisher. So next I'll talk about the properties and the applications of this concept. So the first result that we have is about no cloning theorem for pseudorandom states, and because it's for pseudorandom states, we call it cryptographic no cloning theorem. And basically the result is that these pseudorandom states are not efficiently clonable, as long as you satisfy the definition that we gave. So so for any family of pseudorandom states with phi k with key k, and some m, and m prime is larger, and any polynomial time quantum algorithm that tries to clone to get m prime copies from m copies, then the success cloning probability is given in this way. So on average of the key space, it will be negligible, so it will be smaller than any inverse polynomial of kappa, the security parameter. And it's actually an easy proof. the basic idea is first you notice that random states are not clonable. That's we all know. So if this pseudo-random states families are actually clonable, then you can use this property to distinguish it from the random hard random case and by swap test. So, for example, if you can make m prime, so that you make 2 copies from 1 copy, then you can use swap test. You ask for 4 copies, and use 3 copies. You start with 1, and you copy it to 2 copies, and use the remaining 2 copies to test whether they are the same. And if you succeed in the test, then you would be able to distinguish whether you're from the pseudo-random family or you're from the hard random family. This, I guess, give you a hint that this might have some applications on money scheme, because no cloning is really important for construction of quantum money schemes. Since our session chair has already done a great job in this first talk of this morning on quantum money, so I just save time and skip all the discussions, but mention that the security of the money scheme is that first you have a verifier so that valid banknotes will be accepted, and then you cannot counterfeit with good probability. And so our result is that you can actually come up with simple money schemes from any pseudo-random state families. And simply the bank would choose a key and use the same states for the money banknote, and there's no like serial numbers. I think it's close in spirit to the quantum coin concept. And the verifier once you know the key, so it's a private key, private quantum money. Only the bank who knows the key can verify. It's just because the state is efficiently preparable, you can undo the computation and check whether you get all 0 state. So you essentially can implement the projection to the state. Because there's complication caused by the verifier, it's not directly a consequence of the cryptographic no cloning theorem that I showed you. We have to strengthen the no cloning theorem so that it can handle oracle calls to the verifier. But fortunately, this can be done. So these 2 definitions are actually equivalent, and then any standard definition of pseudo-random states would give you a scheme of quantum money. We also have studied the entanglement property in pseudo-random states. So if you have a pseudo-random family of states satisfy a definition, and with some security kappa, and usually you can consider a bipartite cut, A and B, as long as A and B are both large, because entanglement will be limited by the smaller system. Then what we can show is that the expected Schmidt rank of these states is super polynomial in the security parameter, so it's at least kappa to the C for all C. We also, from this, we can show that the expected entanglement, like the Shannon, the von Neumann entropy of the reduced state, is a little omega of log kappa, so it's larger than any constant factor of log kappa for any constant C. This is not as good as truly random states. So for truly random states, we have like exponential Schmidt rank and almost a linear in the number of qubits entropies. But I guess this is what we can have because this is very general for all pseudo-random states. So to summarize, I've proposed a definition of pseudo-random states, and I've showed you that, I haven't showed you, but if you are interested, you can look at the details of the paper. There are constructions that satisfy our definition, and we obtain certain properties of this concept, and we have shown a so-called cryptographic no cloning theorem for pseudorandom states, and we showed that you can build quantum money schemes. There are private quantum money schemes from this concept, and we can show that there is entanglement, although it's not optimal. But I guess this is all that we can show now. And so there are some interesting open problems. We have been talking about pseudorandom states, but they're like, you can also consider pseudorandom unitaries, and the definition would be obvious, but as we are aware of, there's no proof that these things exist. But of course, there are candidate constructions, but we don't know how to prove that they are pseudorandom. The second question is about the Coulomb secure boundary functions, and so our result is like if you assume that Coulomb secure boundary functions exist, then you have pseudorandom states, but it seems to be necessary that you at least have this Coulomb secure boundary functions, but from the definition of pseudorandom states, it's kind of hard to extract a function from the state family to show that it's actually a necessary thing, that you can actually define the one-way functions from pseudorandom states. And we hope that this concept would have more applications, and so that's all I want to tell you, and thank you for your attention. And we also have multiple PhD positions at UTS, and if you are interested, please contact me, and you can, if you scan this code, you can have information about all our colleagues in UTS who work on quantum information, and you can contact them directly. Thank you for your attention.
Thank you. We have a time for a few questions.
Thank you for that nice talk, and I just want to ask, like, there are some pseudo-randomness concept, like.
Sorry, where are you? Okay.
Okay. So there are some pseudo-randomness concept in the like quantum circuit named unitary design. So is there any correlations with your pseudo-randomness concept to that one?
Yeah. So. It's kind of related, but unitary design or T designs, and on one hand, they don't have this computational indistinguishability. You usually have like some certain distance, but also they would only tolerate certain fixed number of copies, the states or unitaries to look random. For our construction, it's any arbitrary polynomial number of copies. When we try to find applications, we actually look at what unitary designs and T designs have been doing, and try to see whether if you replace these concepts with pseudorandom states or unitaries, it will give you something interesting.
Okay, and the second question is, is there any entropy relations, like if the state is genuine randomness, it's in a hard measure, then Eve has no information about the state. So if the state is pseudo randomness, can Eve have some information about the state?
I don't think I understand the question. Can you see it again?
Sorry.
Maybe we could discuss offline.
Like when we discuss security, we want to know that how many information Eve control about the state. So how can we understand security in this pseudo-randomness framework? That's one.
Sorry, I still don't get.
Maybe we can discuss later.
Yeah, we can discuss offline.
Any more questions? So I'd like to ask one last question. So in your paper, you show something that you can use these pseudorandom states to verify, right? That if you have lots of copies, basically you can test whether another state is that state using the swap test, right?
Right.
And I was wondering whether you can turn your private quantum money scheme to a public quantum money scheme which
It
would
would
be
be fantastic.
extremely, yeah, it would be extremely weird that only rich people can verify money, which would be kind of weird. So if you use the stash that you already have to verify the next quantum money state, that makes sense?
I'm not sure. So I guess it's only for the definition that we ask for an arbitrary number of copies, and this is like a very strong definition. And you have to, when you construct these families, it will be difficult. But once you satisfy all the definitions, then it will be an advantage for the application because you have like a stronger condition that you can use. And this is the condition that we derive these cloning properties and all the other properties that we know that they are can be used as money states. All these properties are coming from the definition. But it's not saying that in order to verify, you need all these many copies. You just need to know the key, and you just undo the computation and see what's all zero state, and you're happy. Otherwise, it's just a projection on the state. So.
Okay,
Yeah.
I'll ask you offline. Thanks. And let's thanks the speaker.